Hello everyone, so today I wanted to share with you a tool that I created during my time as a math tutor. This tool is designed to help students grasp some key concepts in mathematical optimization more effectively. And as many of you know, that machine learning relies heavily on some mathematical disciplines, including linear algebra, probability, statistics, optimization, and calculus. So that's why I wanted to share with you this tool, and hopefully you find it interesting. So basically it's a web application for solving optimization problems using Streamlit. It's straightforward and simple to use, and I will show you later on how to do that. For now, you can only use it to solve optimization problems with only one equality constraint and in 2 dimensions. And that's obviously because we can't consider more variables when plotting functions. And by using this tool, you will get a clear and intuitive understanding of the optimization process. And recently, I've added to it a feature that utilizes large language models to generate insightful reports, and another small feature that involves using a very well-known optimization algorithm in the machine learning world. So in a nutshell, this tool would help you understand the concept of optimization under constraint, and it also assists you in solving the problem analytically using the Lagrange method. So we'll cover all of that during this video, but one more thing to note before we start is that I chose to use Gemini as the large language model in this application for both text generation and OCR. I've tried some open source large language models that I was able to run locally, but their performance was really bad to say the least, especially when it comes to solving math equations and do some math calculations. And even the version 1 of Gemini Pro wasn't performing well, so that's why I went with Gemini 1.5, and the result was really impressive, and you will see that later on this video. But don't worry, for the time being, the Gemini API has a free tier, so you can get your API key and try it for yourself. But of course, there are some limitations to its usage, and hopefully in the near future we would have better small-sized large language models, and I will integrate some of them as an alternative to the Gemini option. Okay, so without further ado, let's get right into it. Alright, so first of all, what is an optimization problem and what do we mean by constrained optimization? Of course, if you already know these topics, you can skip to the tool demonstration. But for those of you that are not familiar with this concept, let me talk briefly about them so that you understand later on what we're doing with the graphical solver tool. Alright, so optimization problems, like many other type of mathematical problems, are very simple to understand. Yet in many cases, it's very hard to find the solution for the problem analytically. And that's why we develop what we call numerical solvers. And in machine learning, we have several numerical solvers for model training, such as the family of gradient descent algorithms. So the goal of an optimization problem is to either minimize or maximize the function that we usually call the objective function, meaning that we're looking for the points where the function reaches its minimum or maximum. And in the machine learning universe, we're familiar with the term loss function, and that usually constitutes a part of the objective function of an optimization problem in machine learning, because we usually add to it some regularizing term to avoid, for example, overfitting. For instance, we use the mean squared error loss function for linear regression, we use the log loss or binary recurse entropy for logistic regression, and we use the hinge loss for SVM or support vector machines. But as I mentioned, we usually add to them a regularization term to formulate the final objective function of the model. And generally speaking, in the supervised learning framework, the objective function depends on the values of the weights and biases. So the goal would be to find the optimal values for these weights and biases to minimize our loss function or our objective function. Alright, so that's briefly what's an optimization problem. But now, what do we mean by constrained optimization? Well, constraints are limitations that we impose on the searching space. And let me show you some examples to better illustrate this concept. So for example, here we have the ridge regression optimization problem. As you can see, we have the first part here, the mean squared error, and then we have the L2 regularization. And in this current form, the optimization problem is not constrained. However, we can reformulate this problem as follows to obtain a constrained problem. So these 2 problems are equivalent, meaning if we find the solution for the first one, we find it for the other. So in this example, we transformed the regularization term into an inequality constraint, and we impose that the norm of the weights does not surpass a certain value that we choose. And this is a type of regularization that we use in machine learning that limits the weights searching space. And in this case, the set of candidate weights is reduced to the closed ball of radius square root of t. And here's another example of constraint optimization in machine learning. So first we have the unconstrained optimization problem for support vector machines, and then we have the reformulation as a constrained problem. But let's take a look at a much simpler version of this problem, which is the hard margin SVM, which supposes that the training data that we use is linearly separable. So here, if you're familiar with the SVM models, you know that we're trying to maximize the distance between the hyperplane and the support vectors, which are the closest data points to the hyperplane. In other terms, we say that we're maximizing the margin, and since that distance is expressed in 1 over the norm of the weights, then maximizing it is equivalent to minimizing the norm of the weights. And that's what we have here in this optimization problem. And as for the constraint that we have here, it represents the decision function, meaning that when we calculate it, it produces a value that tells us in which side the point is and how far it is from the hyperplane. And in this hard margin version of the SVM model, we're imposing that the minimal distance between the hyperplanes and the other points is equal to 1. So this constraint also limits the searching space of the weights and biases to a subset. However, it's often very hard to imagine that subset, especially when we have high-dimensional problems, which is the case for most machine learning models, of course. Alright, so now the general form of optimization problems that you can solve using the visual solver tool is the following. So here we have to minimize an objective function that we call f, subjected to an inequality constraint which we call g. So we've seen the inequality constraints in the previous examples, and now we have the equality constraint, which serves the same purpose of restricting the searching space to a subset or subspace that we call the feasible region. So for example, if we take the constraint function g as follows, then we have the feasible set defined as such, and that is the unit circle. And to solve this kind of problem mathematically, we usually use a method called the Lagrange method. And briefly, this method converts the constrained problems into unconstrained problems using what we call Lagrange multipliers. And using this function that we call the Lagrange function, we can verify certain conditions to find critical or stationary points, which are the only candidates of being the solution for the optimization problem. And finally, by verifying other conditions, we can draw our conclusion about their nature, whether they are a solution for the optimization problem or not. So these are briefly the main steps for solving an optimization problem mathematically or analytically, and we'll take a closer look later on this video on the different conditions that I've mentioned. However, I will refrain from covering many mathematical details as they are not in the scope of this video. Okay, alright, so now let me show you how to use this visual solver tool. So first of all, you need to go over to the GitHub repository and either clone or download the code. And then the installation is pretty standard. You simply create the environment and run the Streamlit application. Alright, so here we are. Now, as I said in the beginning, this is a visual solver tool that you can use to solve optimization problem graphically. However, if you want to generate insightful reports, you need an API key for the Gemini model, and you can use it for free for the time being. So first, here you can follow these steps to get your API key. I already have one, so let me paste it over here. Now first I will start by explaining the different parameters that you see on the sidebar. These parameters you need to set to create the optimization problem. So first here we have on the sidebar 3 buttons for predefined examples that you can use to see how this tool is expected to work. And after that we input our API key here. And then we need to input our objective function and our constraint. So you have 2 options, either to input them manually using Python with NumPy syntax, or you can upload an image that contains the definition of the problem written in LaTeX or using the math notations. And with this button you can extract it automatically using, of course, Gemini. Then we have some parameters that are required either for running the visual solver or for plotting the results. So first you need to define the boundaries for the x and y variables. You can think of this as the domain of definition for the objective function. Then we need to select the appropriate numerical precision for both x and y axes, which will be used later on to create the mesh to plot the different surfaces. and also the precision multiplier parameters, and that is a multiplier used to increase the precision of the solver, but it is not used for plotting. So for example, the precision of the x-axis here is set to 100 and the precision multiplier factor is set to 10. This means that the precision used to solve this problem is actually 1000, and I've introduced this multiplier to increase the solution precision without increasing the computation cost too much. Since the surface plotting is a costly procedure, and if we increase the precision or resolution of the mesh, the time and memory usage would increase dramatically. But using this multiplier, even if we increase the multiplier to 100, the precision would increase. However, it wouldn't affect the execution time as much. And finally, here we have the visualization parameters, and these basically are buffs or paddings used along each axis to increase the field of view. These parameters only impact the visualization, and I would recommend to start with small values like 1, 2, or 3 along every axis. And then after you have your initial plot, you can adjust these values as you wish. Alright, so now let's go to the second page here and run the graphical or visual solver. And by the way, I would recommend that you start always with the solve visually option alone without generating the report, as it consumes your API requests. And then if you want to adjust the visualization parameters, you would have to regenerate the whole report. So it's better to start with the solve visually option only. Okay, so here the first two plots represent the constraint function and the feasible set, and the third plot represents the local view of the optimal solution. So let me explain a little bit how this is achieved. So first we take the constraint function and we plot the level 0 of its contour. That is the curve that you see here that is obtained by the intersection of the function surface with the hyperplane of equation z equals 0. And we need this specific contour level because we always define the constraint as the function g equals 0. And of course, don't forget that we're minimizing the objective function f, meaning that we're looking for the x and y coordinates that gives us the minimal value. So the search space is initially r squared, or the whole plane. But with the constraint that we imposed, the search space is reduced to the set of points on this specific curve. So we will only be looking at the points on that curve to minimize the objective function. Alright then, so now we know that our objective function depends on two variables. That means that the plot of the function would be a surface in 3D. And because of that, we need to extrude our feasible region along the z-axis, so that we can visualize the intersection between it and the objective function surface. So here we have the surface plot of the objective function, and then we add to it the constraint. Now we can see the intersection points, which represent the z value for each point in the feasible region. And since we have all the z values, we can look for local minima, which are represented here in yellow, and the smallest of the local minima is considered the global minima. And here, since both local minima has the same value, we say that the optimal solution is achieved at 2 points. And we can zoom in to read their values. Here we have 1, 1 and -1, -1. And you can see that we have numerical inaccuracies, but we have a very good approximation of the solution. Okay, good. So now let me change a little bit the visualization parameters. So for example, now the z-axis goes from -3 to 5. So let's set the z buff to 7, 7, and let's rerun the visual solver. Okay, so the z-axis new limits are -5 and 9. And you can see that the extrusion of the feasible region no longer reaches the limits of the z-axis. So then we need to adjust the z extrusion buff accordingly. Let's set it to 7. So there we go. So basically the buff's parameters gives you some control over the axis limits. In other terms, it allows you to choose how much you want to zoom in on the solution. Very well, so now let's generate a report for this optimization problem. So simply we click here. It's going to take about 3 minutes. So I'll speed up the video so you don't have to wait. Alright, so let's see what do we have here. So I'll first put on the right side of your screen the different steps that I indicated for the large language model to solve this optimization problem. And let's see how it performed. So the first step is to check the feasible region, whether it's empty or not. And we do that so we can see if we can aspire to find solution for this optimization problem. So here for the first step, the model just gives us an example of a point from the feasible region to prove that it is not empty, and that's an acceptable answer. So let's move on to the second step, in which we need to define the Lagrangian function and then solve the system of equations given by the gradient of the Lagrangian equals 0, which would give us the critical points for the optimization problem. So let's see what we have here. Alright, so we have the Lagrangian definition, and then we have the system of equations and the different solutions. So that's a clear answer, and we can move on to the next step. So the next step is to check for critical point regularity. So to do that, let's see what we have here. So first of all, we have the constraint function, and then we evaluated the gradient of the constraint in each point. And since we obtained non-zero values, then we say that the critical points are regular, or the constraint is active in the critical points. Alright, so after that, the first step is to find or determine the nature of these critical points, whether they are solutions or not for this optimization problem. And we do that by verifying two types of conditions of second order, the necessary and the sufficient conditions. And we're not going into details of these optimality conditions, but the main idea is to check the definiteness of the Hessian matrix, which is defined by the second order partial derivatives of the Lagrangian function. So this would give us an idea about how the objective function is behaving around or in the neighborhood of the critical point. If the objective function is convex, we say that we have a local minimum, and if it is concave, we say we have a local maximum. And if it's neither this or that, then it's not a solution or a candidate to be a solution for our optimization problem. Now let's check the report for this step. So here we have the Hessian matrix, and here we evaluated in each critical point. And we have conclusion. So for the first point, it concluded that the matrix is positive semi-definite, so further analysis is needed. And for the second point as well. So we would need to go to the next step to obtain more information about the nature of these points. And in the next step, we also work with the Hessian matrix, but we check for the definiteness only in the feasible directions. And let's see how it is performed here. So we have the feasible directions defined as such, and then for each critical point we check again, and we can see here that this sufficient condition is verified for the first point, so we have a local minimum, and it is also verified for the second point, so we have also another local minimum. And finally we have the generated conclusion about the optimization problem. And that's basically how you can solve this optimization problem mathematically. I hope that's clear. And as you can see, the Gemini 1.5 did very well. Now I know that some of you are not familiar with these calculations, but don't worry, now we're going to see something that you most likely are familiar with, which is a very well-known optimization algorithm. And we're going to see how to use it to solve this constrained optimization problem. So let's move on to the final page here, which is for performing projected gradient descent. Alright, so you know that gradient descent is an algorithm used for machine learning models training. And generally speaking, it achieves that by taking small steps in the opposite direction of the gradient of the objective function until it reaches a minimum or a solution for the problem. But we can't use that version of gradient descent in constrained optimization, because the update rule doesn't take into consideration the constraint that we impose, and so we need to modify the update rule for gradient descent. After each step taken using the gradient of the objective function, we can project that point into the feasible region. That way we include the constraint into the gradient descent algorithm, and this modified version of gradient descent is called projected gradient descent. Its implementation is pretty simple, like gradient descent. However, its convergence to the solution of the problem is not always guaranteed. The optimization problem would need to verify some convexity and some regularity conditions so that the projected gradient descent would converge to a solution. So let's see now for ourselves this algorithm in motion. So here first we have some parameters that are self-explanatory. We have the starting point or initial point. We have the maximum number of iterations. We have the step size for the gradient descent, and then the convergence tolerance. Now the last one here, that is the grad field scale. It is used for visualization to scale up or down the size of the plotted gradient field of the objective function. We can leave it as it is for now, and then we can adjust it if we want to. So let's run this algorithm. So here we have three figures. The one below is similar to what we've seen earlier, and the two on the top shows different representations of the objective function in 2D. The one on the left shows the contour plot, and the one on the right shows the gradient field. Now using this slider below, we can visualize the steps taken by the algorithm, and let's take a few steps and see what happens. Okay, so we can see clearly here that the line moved along the gradient direction, and then the point was projected to the feasible set. Okay, so now let's move on to the final steps and see what happens during the last iterations of this algorithm. Alright, it's not that clear, but we can zoom to see the iterative process. So every time we go down towards the minimum of the objective function, then we project until we reach the optimal point, and that is exactly when the gradient of the objective function is normal to the feasible region curve, because in that case, the projection onto the feasible region returns to the same point where we were before we take the step along the gradient direction. So we keep moving back and forth between the same 2 points, and that is exactly what we mean here by convergence. And that is actually natural to happen when converging, since we've seen before that the necessary condition of optimality is that the gradient of the Lagrangian function is equal to 0. And when we rearrange the terms of that equation, we can see that the gradient of the objective function is collinear to the gradient of the constraint, meaning that they have both the same direction, and that is exactly what we concluded visually. Now here in this figure, I've plotted the gradient of the objective function at the optimal point, and you can see that they are not collinear, so to speak, but as I said, that this is only due to some numerical inaccuracies, so you don't need to worry that much about that. One last thing to note here is that this method depends heavily on the starting point. So if we choose, let's say, a point that we start with that is closer to the -1, solution for this problem, we would converge to that solution. And also this algorithm has no way of avoiding local minimas, so you should keep that also in mind. Now here's another example solved using projected gradient descent. You can see that the gradient field arrows are too big, so then we can use the scaling factor to reduce their size. As for this example, if we start anywhere here, or even closer to the other contour line, we would not achieve convergence. Now, I've tried solving numerous problems using this tool, and for the most part it works well and as expected. But since it's a graphical solver, it will fail sometimes due to numerical inaccuracy or lack of precision. Alright, so that's it for today. I didn't want to go through the code since it's very long and probably boring for the most part, but as I said, you can find it on GitHub, and if you have any question about it, feel free to ask. I'll try to make this tool solve a wider range of optimization problems, so stay tuned for that if you're interested, of course. Alright, so that's it for this video, and see you in the next one.